in this
or
course. Okay,
class.
so let's start. Okay.
Okay, so I'm thinking about starting with the prerequisites that we need for this course. Most important things that we need are
Joe, can you
the
share the board?
yeah, I'm sharing the board now. Okay, sure. So the most important mathematical skills that we need to develop, or mathematical intuitions that we need, are about vectors. Okay, vectors. Then we need to know, of course, we are dealing with electromagnetism. So the basics of electromagnetism is actually the concept of Maxwell's equations. Maxwell's equations. And as I said earlier, we are dealing with Fourier transforms. So we have to learn about Fourier transforms also. So these are the major mathematical and physical prerequisites that we need to know, especially the dealing with vectors a little bit and the Fourier transforms. So in the sense, we need to know how to take the derivatives of the vector and how to integrate the vectors and all those things. So I am inclined, or I thought that we can start with these vectors, and we will move. And we will first discuss a little bit about we are now discussing a little bit about derivatives of vector. There are different types of derivatives which results in vector and which are done on vectors. So these derivatives include what we call gradient, then curl, then divergence. So these, most of you have understanding about what this means. These concepts are actually your graduate concepts. So we will refresh upon this and try to get intuitive, what we call as a physical feeling about what these entails or what these vectors are mean. So let's start. Okay, so we'll start with what we call as gradient. Okay, so Vinith, what do you understand by gradient? What do you remember about of a vector?
Meaning change in all directions.
Not exactly. So you know about scalar fields. Can you tell me about a little bit about scalar fields?
Scalar fields have different values at different points of space.
Points in space, isn't it? So a simple example I would like to talk about is, let's take an example from electrostatics itself. Okay, so we know about potential, isn't it? Potential. So we have learned about an electrostatic equation, del phi, or we can say del V, or some may call it as grade of potential, is negative of electric field. Most popular way of writing is actually E is equal to negative grade of V, isn't it? So what is it? So if you think about, let's learn how to find gradient of a vector. Okay. So whenever we are dealing with
scalar
gradient of a scalar field. Okay. So whenever we are dealing with this symbol, it simply means it's dou by dou x into in x direction plus x dou by dou y, partial derivatives in y direction plus dou by dou z in z direction. This is what this operator means. This is actually an operator, like just like a plus or minus or something like this. This is an operator which which will operate upon a scalar or a vector. You can think of this as a machine. This machine can take a scalar or a vector as an input, and it has different modes. One mode is gradient mode. Another mode is a what we call as a divergence mode, another mode as a curl mode. Depending upon this, it will take different input, a scalar or a vector, and spit out their own what we call as vector or scalars. Okay.
Oh, okay.
So let's look at what this. So suppose we have a function, let's say v. Okay, v is a scalar, which means we usually write as v of r, which means that for each point in a three-dimensional space, v has a particular value, isn't it? Suppose we have a x, y, z plane here, and at point P1, we have, suppose we can have the potential is let's say 9 volt, and at point P2, the potential may be, let's say 19 volt or something like that. Okay. Okay. So a scalar field simply means a number or a function which has different values at different points in space. That's what a scalar field is. So a gradient of a scalar field will be written like this. So we can say gradient of v is simply equal to, we will write it as partial derivative of v with respect to x in x direction plus partial derivative of v with respect to y in y direction plus partial derivative of v with respect to z in z direction. So actually the output of gradient is always a vector. Output of gradient is always a vector. Gradient is always a vector. Okay, that I think you understood, isn't it? Now, next thing is, what is the significance of this vector? Okay, so what is the significance of this particular vector? That's what we need to find. Okay, so we usually say that gradient of a scalar function is usually a vector in the direction of its largest increase. Okay. Have you understood? Do you have any doubt there?
You should explain it more.
Yeah, I'll explain with an example. Okay. Gradient of a gradient of a scalar gives a vector which points in the greatest increase in the scalar. Suppose so. So as I said earlier, we had scalar functions. Functions or a scalar field is a function which takes each point in space and associate it with a number, isn't it? So if you have a three-dimensional space x, y, and z, this scalar will have different values at different points, isn't it? And there will be a particular direction in which this scalar will increase maximally, which means that suppose let's take different directions. Okay, this is one direction in which the number the value of scalar is increasing. Let's say the rate of increase with respect to this in this direction, it's let's say is 12 units. per 12 units. Okay, and in this direction it may be, let's say, 15 units, and let's say in this particular direction it has the greatest increase. Greatest increase, that is actually what the greatest increase, that is, let's say, 500 units. Okay, so gradient of a vector actually gives this actual vector itself. Actual vector in the sense the magnitude of the vector will be equal to the highest rate of change, and the direction will be the direction of greatest change. Okay, it's very okay. Let's attach a physical meaning to this. Okay, you earlier I told you gradient of V or negative of gradient of V is actually equal to electric field. So in electrostatics we have studied electric field always points in a direction which is equal to the greatest decrease in voltage. Do you remember? Potential. That's because of this. That's because of this property. So actually, this negative sign actually says that the greatest decrease in the direction. Okay, have you understood that? I hope you understood. Okay. Okay, so electric field E is actually equal to negative gradient, which, what does it mean? Electric field. Okay, what does it mean? It means that negative. Okay, the electric field is a vector. Electric field is a vector which points in the greatest decrease of potential. This can be seen. Actually, this can be attributed to mechanics also, in the sense. So we are dealing with some purely theoretical concepts like the path of least action. Okay, path of least action is also connected to this, but we are not going in depth into that. Now let's move on to the next concept, that is divergence.
We can also see this in the light of gravitational theory.
Yeah, gravitational field also. Why the so gravitational field always points in the greatest decrease in the gravitational potential. So that's what this means. Okay. So gradient of a scalar will always point in the greatest increase in the vector. Since here we are having a negative sign, it becomes the greatest decrease. Negative. Okay. Okay. Yeah. Okay. Have you understood this idea?
Okay. I got it.
Okay. Now let's move on to the next topic.
Gravitational example would be great if you draw the picture of an earth or something. I will discuss it in terms of gravitational picture. So you in 12th class or in 12th standard we have learned about gravitational field and all those things. So it's actually okay. Suppose you have an object, a ball, particular ball here. Okay. No, don't place object. Just draw the earth.
No. I will. Yeah, I will show you why. Okay. Yeah. Let's move with your idea. Okay. What is your idea? Let me hear it.
No, just draw an earth.
Earth.
Just point the gravitational field.
Yeah.
And that field is in the direction of negative potential. That's it. Just the idea.
So this is the Earth, and the gravitational field will always be towards the center of the Earth. That we already know, and this is the direction of the greatest decrease in the potential of the gravitational
atmosphere.
In the atmosphere also.
From the atmosphere, exactly.
Yeah, from the atmosphere.
direction. Yeah, that
gravitational field.
the gravitational field. Yeah, this is the this will be the direction of gravitational field. What
Just
we
like
call
gravitational field.
gravity. Yeah,
Just like gravity.
gravitational field, and this will be the direction. So we know that the gravitational potential will be high, will be larger when we move away, and as we move towards the Earth, the gravitational potential decreases. So the gravitational field is actually in the direction of the gravitation, against the or will always point to in the direction of the greatest decrease in gravitational potential. I hope you understood. Okay, now let's move on to the next, what we call next culprit or next next
Don't say bad words.
derivative. It's not a bad word, actually. It's the words.
It's a good word.
Yeah, divergence. Okay, divergence, or we write the dive or dive or del dot something. Okay, now divergence is another mode of that operator. So it acts. Okay, let's go. It acts on a vector. It takes a vector as an input. Okay, it takes vector as an input, divergence, and gives out a scalar as the output. Okay, this the input is a vector and the output is a scalar. Usually it is written, suppose if you have a vector, let's say a specific, let's say a vector f, let's call it as fx. Fx means x, the component of x in x direction, plus fy ey plus fz ez. Usually in India, we usually write this as like fx I cap, fy j cap, and fz k cap.
So don't write that.
Yeah. So actually, different countries have different notations. So it doesn't matter.
We'll stick with the EXEY.
EXEY.
Standard in
Yeah.
mathematics.
Yeah, that's in standard mathematics. Okay. So divergence will be, we can write as del dot f, could be written as partial derivative of x component of x with respect to x, partial component of y derivative of x, f with respect to y, and partial derivative of z component of f with respect to z. When we will add it. A more detailed version, way of saying this is actually like this. You can simply write it as dou. As I said earlier, this is actually, this del is a operator which is written like this. You can simply consider this as a
just dot product, an inner product. Right?
Yeah, inner product. Yeah, dot product or an inner product. We can simply consider this del operator as a vector itself. Dot f x e x plus f y e y plus f z e z. When you take a dot product of this, you will simply get this answer. Okay. Now here comes. This is how we take the divergence of a vector. Okay, so now let's talk about let's talk about the physical meaning or physical intuition. Okay, so in order to understand that, I would like to move our attention to a different way of defining this vector, this divergence. Okay, there is a different way of defining this divergence using an integral. Okay, let's look at that. According to that, we can say
suppose divergence of a vector f, divergence of a vector f of r could be written as, there is limit delta v tends to 0. Okay, limit delta v tends to 0. So yeah, integral, closed integral over volume, okay, f dot dA, okay, f dot dA.
You should write it much more bigger.
Okay, I will okay, I will make it much bigger once again, into delta v. So let's make it a okay, let's make it a little bit bigger. This is the, can you see?
Yes, sir.
Okay.
This is the integral form of
divergence. Okay. Now, most of you have from your bachelor's, most of you have, or most you might know what this means. This particular idea means. What is it?
it's a closed loop integral, right?
Gaussian type integral. Yeah, Gauss-Law type integral.
Closed loop integral.
Yeah, it's a closed loop integral. So it's actually, suppose you have an infinitesimally small volume. Okay, infinitesimally small volume. Okay, that's what this delta v is, limit delta v tends to 0 is for. Okay, now what is this f dot dA will give you? F dot dA will give you the amount of flux through this volume. Have you understood? Okay, amount of flux through this volume. So what divergence give? What does divergence actually give then? Can you
flux through an infinite volume?
Yeah, or when we are yeah. So divergence,
some kind of flux density or something.
Yeah. So actually, divergence is a scalar field equivalent to the flux through an infinitesimal volume. Have you understood? Okay. So divergence of a vector will give a scalar which is equal to the, okay, let me write that. That will be divergence.
You should write their
the
integral formula of,
yeah,
before that.
Yeah, I'll write.
Just delete that physical and write the integral formula. Integral formula of divergence.
Integral formula and physical meaning.
Okay.
Okay. So divergence of a scalar. Divergence of a, not, we cannot take divergence of a scalar. It's actually divergence of a vector is a scalar which gives the flux through an infinitesimal volume. Are you able to follow? An infinitesimal volume. When you think about in this way, the Gauss's law will become apparent, isn't it? Gauss's law of electrostatics and all those things will become apparent, isn't it?
Then you should explain through diagram, I think.
Yeah, I will explain through diagram. Suppose you have, okay, a huge cube. I have a huge cube.
Like a Rubik's cube.
Yeah, huge. Yeah, exactly like a Rubik's cube. I have a small part here. Okay, infinitesimally small part here. Okay, so suppose you have a vector field through all this. Okay,
a flux through all this. Okay, so actually when you integrate this divergence over the whole volume, what will it give? It will
Total.
give, yeah, total flux through the whole volume, isn't it?
Yes, yes.
Divergence is the divergence is the flux through an infinitesimal volume. And if you add up, or if you stack it up and add the whole thing, what will it give?
Divergent flux through the entire thing.
So, yeah, flux through the entire thing. What is it given as E dot D or F dot D? Isn't this the Gauss's theorem? Gauss's theorem in integral form. Have you understood this idea?
Okay, wait. So in the integral formula, you are moving that 1 over del V, 1 over delta V to the other side and integrating.
Yeah.
No.
Yes, it's a.
Is there
Exactly.
dV?
Yeah, you have, when you integrate, you are integrating over the whole
Yes.
volume.
Okay.
Have
So
you
this
understood
can
this
be
idea?
obtained from that integral formula.
Yes. We
Okay.
can. And so why I defined it in such a way that because it gives you a more, what we can say as the more physical meaning, or more physical understanding about what divergence means. We usually, when in our education system, we just usually take what this is divergence, but the actual mention of what this entails is more than often is left to our own imaginations and all those things. Have you understood that? I hope you understood. Do you have any doubts here?
Okay, so that means Gauss theorem
Is a natural consequence, actually, when you
when you think about it.
Yeah.
When you integrate this thing. Right?
Yeah.
Okay.
Okay. Let's move on to the next one. Curl of a vector. What is curl of a vector? What do you understand by curl of a vector? From bachelor's or master's,
Curl
what we have
is
learned?
del cross a vector that you should give a vector.
Yeah. Curl is another operator, another mode of this differential operator. It takes the input is a vector, and its output is also a vector. Okay, now what does it mean? What does it actually mean, curl? Or how? Let's look how to find curl. How to find curl. So to find the curl of a vector, actually, it's simple as multiplying two vectors. Okay, we can write del cross f or curl of f, or we usually write curl f is actually cross product of these two vectors, dou by dou x in x direction, dou by dou y in y direction, plus dou by dou z in z direction, cross fx ex plus fy ey plus fz ez. The simplest way of doing this is actually using a determinant, isn't it?
Yes.
So we can write, the most easiest way is using a determinant. So you will take it as, you'll take ex here, ey here, and ez. Okay, then dou x, dou z.
then fx, fy, fz. Now, this also you can take the derivative, find this determinant, and you will find the value of the curve. Hope you understood this.
Yes.
Any doubt here?
No.
Okay. Now, so curve has another word. Curve is known by another word also, rotation or rot. Have you heard about a rot of a vector? Rotation of a vector.
I have no.
Okay. So what is this? What is the connection between curl of a vector field and this rotor thing that we are talking about? Okay, so let's talk about it. Okay, in order to understand that, we are going to define the curl of a vector in just like before, an integral form. Okay. Hello.
Okay.
So it's a pretty complicated definition, but I will give you what you can say. I will give it to you. Yeah, I will give you the physical meaning. Okay. Also that. Okay. Integral form and physical meaning. And this actually will give you the idea about Stokes theorem also. Okay, integral form of curve. Okay, in order to understand that, I am actually going to define an area. Okay, so an infinitesimal area which is actually bounded by a small loop. Okay, a small loop. Okay, this is that loop. Okay, and an infinitesimal point, and that loop is given by a small ds. So ds has a direction. This ds gives us the
small arc length.
Yeah, small arc length. Yeah, we can say. And I am tending, this is that area delta A. As usual, we will assume this will tend to 0. This is the direction of our R. And we also need a direction like this.
Some normal, right?
No, yeah, some normal. Yeah, this is normal, and let's call it as N. Okay, any doubt in this figure? I don't think so. There should not be any doubt. Okay, we can also make okay, yeah, and
so that area is actually in the direction of that normal, right?
Yeah,
the normal is the perpendicular to that area.
Yeah, and let's assume that we have let's say something like this. Okay, I hope you are getting the idea. Dot something like this. Okay, this normal is actually, so it's very difficult to draw it in a three-dimensional way. This normal is as normal to this plane here. Okay, so the integral form says that n dot curl of the vector f of r. Okay, n dot curl of a vector is actually equal to limit delta a tends to 0. Okay, delta a tends to 0 in closed integral over the loop. Delta a.
Delta a means
that closed integral.
Small area. Right?
Small area. Yeah.
So don't write delta a.
It's a actually this is a standard notation. Del a means this area enclosed by this particular loop. Del a means area enclosed by this ds. Okay, divided by delta a. So what actually it gives is the curl of the vector will is a vector which shows us how much. So this f of r is
meaning that small area is del A, not delta A, right?
No, actually, if I write something like this, okay, let's retrace a little. If I write something like this, 0 delta A f dot ds means the area enclosed by this ds, this loop ds. This is a standard.
That's what I meant. Meaning that area you have drawn is delta.
Del A is actually delta A here itself. Okay. Similarly, if you write f dot dA, it means that we are integrating over the volume enclosed by this dA, small
okay,
a.
I got it. What's that big delta?
Big delta is the area around it.
Of that
okay,
some surface.
Yeah, 1 second. There is a small mistake here. Of delta A. This is a standard notation. Okay. Now here, so this is the integral form. Let's talk about the physical meaning.
You should zoom that equation.
Yeah, I will zoom, make it larger. Okay. First, let me just put it down. Put some. Okay. Large. Let's make it larger. Can you see?
Okay, so that integral is over del of cap
delta. Yeah, big delta A. Okay. Now, what do you understand? What is the physical meaning? Okay, what is the physical meaning of this whole thing? Physical meaning of curl. Okay, so we know that curl gives us a vector. So it has what we call magnitude and direction, isn't it? Now, the magnitude of this f of curl of f of r will give the strength of rotation, which means that this in this surface this vector f has some rotating effect, which means that on the surface this vector field, which vector field means at each point on the surface the vector has a particular magnitude and
so
a particular
direction. Just write f of r there, just somewhere around in that field.
Yeah, f of r. Okay, so it has different. It has different orientations in different directions like this. Are you able to follow?
Okay, is that rotating effect due to that taking that curve because we are using that
not exactly. We are using the curve to find the rotating effect. Okay. Magnitude of the curve will tell you how much rotation f of r, the vector field f of r has on the surface delta.
Okay, that's what I'm asking, because that rotation effect has to come from somewhere, right? I'm asking that is that effect due to that cross product, like that cross?
No. It's actually it may be due to some other values. For it may be the nature of the vector. So curl of a vector actually talks will give you will show you whether the f of r or the vector has a rotating nature or not. Okay. And the direction of the vector.
So the curl will tell you whether it has
rotation and the magnitude of the curl. So if curl is actually equal to 0, okay, we call those vectors are irrotational.
Yes, I remember.
is equal to 0 means implies F is irrotational. You remember?
Yes.
Similar. So only when this F has the vector field F has a rotating effect, then we can have the curl. It tells about the rotating strength of a vector at a particular surface. Okay, the magnitude of the curl. Okay, and direction. What is direction? What will be the direction? Direction is actually in the direction of axis of rotation, which is given by our right hand screw rule.
Okay.
Direction of axis given by
direction of axis
given by right hand screw rule. You understand this idea of curl?
Okay. What you said is that the curl will tell you whether a vector field is rotating.
Yeah, whether a vector field is rotating or not. For okay, you may get an intuition about this when you think about it like this. Suppose it's not we cannot say that it is exact, but when you think about it like this, suppose you have a circular loop of current like this. Okay, circular loop of current. Okay, current, what will it give?
It will give magnetic
field. Yeah, a magnetic field in the direction of
direction
given by right in the direction of axis of rotation, and that direction is given by right hand screw rule, isn't it?
Yes, sir.
Now think like this will be the direction of magnetic field, we can say, isn't it? This will be the direction of magnetic field. This is the direction of current I. Okay, now we already know that there is a relation like curl is equal to dou B by dou T. We will talk about when we are talking about Maxwell's equations. So you can think about it like this: a rotating electric field will give rise to a magnetic field in the axis of rotation. Okay, so essentially, curl of an electric field will give you what? Magnetic field.
Okay.
You can think about it like that. Have you understood the idea?
Okay. It is similar to that rotating effect.
Yeah,
because
it's a
when you rotate, it's like making pottery. So when you rotate, the clay just moves.
Yeah, moves up.
The upward direction. Okay. Similarly, when the current is
in the opposite
rotating,
direction,
the curl will be upward. That's why the curl gives the magnetic field.
Yeah.
Okay. So you need to first learn pottery before
learning this whole thing. So you got the idea. So let's stop for today. I hope you understood, and we can discuss much more of this in later classes.
Upcoming classes.
Upcoming classes.
Okay, Joe.